Ladies and gentlemen, if I could please have your attention. Thank you very much for coming and joining us here in the Geological Society London this afternoon. My name is Dr. Sarah Gordon, and I'm a member of the council here at the Geological Society. Before we get going with this fascinating lecture that we've got lined up for you, just some housekeeping. Firstly, as far as I'm aware, we have not planned an interruption to this fabulous lecture in the form of a fire alarm. So if you hear the alarm sound, then it's advisable that we perhaps leave this room, going out by the various exits that you can see round about you. Secondly, if anybody here has a mobile phone, fantastic. However, like in the vacuum of space, we don't really want lots of sound to interrupt us, so if you can please make sure that it's switched to silent or off if preferable. So thank you very much for coming and joining us here this afternoon at the fourth of our London Lecture Series. As you can see, maybe when the slides change, we're going to be talking about space rocks, rockets and robots exploring our solar system today and tomorrow. And it's my pleasure to introduce you to our speaker, Dr. Caroline Smith of the Natural History Museum. Now, any of you who have come across meteorites in the past will know that they provide us with a glimpse of what was going on in our solar system 4.56 billion years ago. So at the birth of our very special star, the sun, what was going on then was this swirling cloud of gas and dust that condensed to form our planets and various rocks, etc., that form our solar system as we know it. Now, as human beings, we have been firing things into space to try and explore our surrounding environment. So since the 1940s, we've been firing rockets, satellites, dogs, rabbits, mice, insects, frogs, guinea pigs, monkeys, and even fish into space to see what happens to them. We've also managed to get a few people up there as well and bring them back. However, when we start talking about exploration today, most of our space exploration is undertaken by robots. And what we've been doing is we've been sending robots to the likes of Mars, to different moons within our solar system, different asteroids, and even comets. So Dr. Caroline Smith is head of Earth Sciences Collections and the principal curator of meteorites at the Natural History Museum here in London. Her experience and expertise is phenomenal and has been recognised with the award of an Aurora Fellowship from the UK Space Agency. Caroline works with leading industrial, academic and international space agencies to study and plan future solar system sample return missions to the likes of Mars, Phobos, the Moon and various asteroids. Caroline has studied a wide range of different meteorite types, some of which I've had the luxury to study with Caroline. However, her main interests and research areas at the moment lie in the realm of planetary differentiation and extraterrestrial alteration processes. So, ladies and gentlemen, please put your hands together for Dr. Caroline Smith.
So So thank you very much, Sarah, for such a very nice introduction, and also for stealing some of the things I was going to talk about in my talk. So hopefully maybe Sarah's given you a flavour of some of the aspects that I'll cover in this talk. Hopefully I won't go on for too long. I realise we're on quite a tight time scale. I did realise, so what happens, the Geological Society contacts you and says, well, you know, we'd like you to come and give a presentation as part of our London lecture series, and they give you some dates. And so I picked this date, and I had to write an abstract. So I thought, okay, what am I going to talk about? So I wrote the abstract. Obviously, that was done before I put the talk together. And in fact, when I was putting the talk together, I realised that actually if I'd covered everything I wanted to cover, you'd probably be still here tomorrow. So it really is a little bit of a whirlwind tour. I'm not going to cover everything that I would like to, but at the end of the talk, there's going to be the opportunity for questions, and I will do my best to answer those for you. So, three main topics I'm going to talk about. I'm going to talk to you about meteorites. Sarah gave you a little bit of a flavour about some of the things that we can learn from meteorites. But meteorites have got such amazing stories. Not only are they space probes, they're also time machines, but many of them also have interesting cultural and societal histories, and have actually played a big role in actually how we study our solar system, and indeed how we actually study and learn about our own Earth. I'm also going to talk about how we have used robotic exploration through launching robots into space to actually study our solar system. And I'll be concentrating on the inner solar system, so bodies within the inner solar system. And this also goes on about the robotic exploration, you know, using these robots to actually how we do things today and how we're going to progress by using robots as pseudo-geologists, as our sort of proxies, as our helpers to go out into space to actually understand better our solar system, how it formed and where it's potentially going, and how we can apply that knowledge potentially to other planetary bodies orbiting stars in other parts of our galaxy or indeed the universe. So I'll start with meteorites. And in fact, my mouth's already going a bit dry, so I'll just grab my water. So meteorites have been known to humans actually for millennia, although at that time a lot of people didn't obviously realise that meteorites were actually parts of our solar system, were actually pieces and fragments of bodies within our solar system that actually record, as Sarah mentioned, some of the earliest processes that were actually happening over 4.5 billion years ago. But we do have meteorites in the historical record, so we know of meteoritic metal used by the ancient Egyptians. I'll talk about that in the next slide. Also in Australia, there are Aboriginal oral histories that actually record the fall of meteorites and the observations of large fireballs that were seen over Australia. In North America, and also in Canada, meteorites have been found associated with, for example, burial things called a burial cyst, sort of a funeral associated sort of spiritual thing, and also as well, actually a meteorite in Canada was actually seen as a godlike object, and visiting tribes used to leave gifts to sort of placate the gods. In Greenland, we have recorded use of iron meteorites as part of tools by the Inuits. So in fact, the image on the bottom there is a knife. It's a hunting knife that was actually brought back by Sir John Ross in some of the first Arctic expeditions. It's actually made of a narwhal tusk, and the blade at the end is actually has got some component of meteoritic metal in it. But the first actually recovered fall that we have, so a meteorite that we know about today, actually fell in Japan in the mid-800s. And that was actually a rather sort of fortuitous event, because this meteorite actually fell into the garden of a Shinto shrine. And the monks recovered the meteorite, and they put it into a box, and they wrote around the box about what happened, and it was sort of left in the Shinto shrine. And people knew about it, but people weren't quite sure whether it was in fact a meteorite. And it was actually only in the 1970s that a tiny piece was taken, and it was confirmed that it was actually a meteorite. So the earliest recovered meteorite we have is from about 861 AD. So I mentioned in Australia, we have Aboriginal histories related with the fall of meteorites. The image here is of the Henri Craters, which are in the Northern Territory of Australia. We can date these craters using the sort of standard methods that we date terrestrial surface processes, and they date to about 5,000 years ago. And that actually was a time where we know there were Aborigines living in that area. The local tribe are known as the Aranda. I'm not going to try and speak the language, but you can see it says like Chindu, China, Waru, Chingu, Yabu. I hope my accent's okay. And that roughly translates as Sunwalk, Fire, Devil Rock. And these craters, there's 13-ish that we can recognise. And when I say ish, some of the features, we're not sure if they're craters or others, but the 13 definite craters. And within and around those craters, iron meteorites are found. And it's a type of iron meteorite called a 3AB. You know, we're geologists by heart, most of us who study meteorites, so we love classifying on the basis of chemistry and texture. So it's just a classification term for this type of iron meteorite. And so the local tradition is that a sun devil came down, a sort of demon came down, hit the ground and produced these iron meteorites. And still to this day, men are not encouraged to actually take water from these craters. So you can see it's a semi-arid area. It's a great place to actually collect water. Water collects in the craters when it does rain, but men do not drink water from these craters because the legend is that if you drink water from the craters, your insides will turn to iron. So even though the local people, the Aborigines, didn't necessarily know that these were meteorites, they were able to sort of relate it to a celestial event. The image on the bottom is some work that was actually recently done. Came out a couple of years ago in Meteoritics and Planetary Science, which is a journal that meteorite scientists like to read. And what we can see here, let me use the pointer. So this is Tutankhamun's sarcophagus. It's actually an original photo, so it's black and white, and you can see there is this dagger here, and this is, the image just next to it is actually a clearer image of the dagger. And that actually, the iron in the blade of that dagger is actually made of meteoritic iron. And that was actually confirmed very recently using some non-destructive tests, something called X-ray fluorescence, which can give you the composition of elements like nickel and cobalt quite accurately. And it was quite interesting because this burial, Tutankhamun, dates from the 4th century before, what's BC now? Before Common Era? I'm still quite old-fashioned, I say BC, but that's apparently not allowed anymore. And actually in about the 13th century, so about 100 years later, this hieroglyph first appeared, which actually translates as iron from the sky. So again, the ancient Egyptians were using meteoritic iron and knew it was from the sky, actually as daggers and also as jewellery. So there's also archaeological evidence of jewellery being made from meteoritic iron by the ancient Egyptians. Now, when we actually get to Europe, the oldest recovered meteorite fall in Europe is the Enca meteorite. It fell on the 7th of November 1492. And again, it wasn't recovered because people knew it was a meteorite and something of scientific interest. It was recovered solely by luck. So around that time, Europe, you know, in the Middle Ages had a very interesting history. Countries were at war with each other and states were at war and regions were at war constantly. And at this time, there was lots of things going on, and there was a major battle going on or about to happen in the Alsace region between the Holy Roman Empire and France, I believe, if my history's correct. And this event was actually recorded by a pamphleteer called Sebastian Brandt, and this is actually a copy on the right-hand side of his pamphlet. So Maximilian was one of the protagonists in these ongoing battles and wars and skirmishes. And when this meteorite fell, Maximilian's advisors said to him, "Oh, you know, Lord, this is obviously a sign, a holy sign from God that you are going to be victorious in the battle." And sure enough, Maximilian was victorious in the battle, and so he ordered the meteorite be preserved forevermore in the town of Ensisheim as a sign of his God-given right to, or way to win this battle. So I often wonder what would have happened if he'd lost the battle. I'm sure the meteorite would have been destroyed, and I'm sure his advisors would have also suffered a rather nasty fate. But we can have a look. This is just a blow-up of that image from the pamphlet from the 1400s, late 1400s. And I love this image because it says there's quite a lot of interesting things you can see. It's not overly clear, but this is the meteorite coming down from the clouds, although I always think it looks like it's actually going up. Here are some knights actually preparing for the battle who saw the meteorite land. So this is actually one of the first documented falls of a meteorite. And as I said, it's very lucky, actually, just circumstances were correct, that we still have that meteorite today. And in fact, we have some in the museum collection, and we still use it for scientific studies all of those years after it fell. But there's a bit of a hiatus, actually, and that's, again, down to society and culture of the time. So prior to the early 1800s, late 1700s, meteorites were seen as nothing of great interest. They were, the best way I can describe them is they were deemed as a scientific curiosity at best. Any scientist worth their salt did not consider them worthy of scientific study. And the main reason for that is people who saw meteorites fall and reported them to the authorities of the time, so the local mayor or the local clergy, were people working in fields. They were the peasants. And everybody knows rocks can't fall from the sky. How ridiculous. What a ridiculous concept that rocks fall from the sky. And these ill-educated people, they're illiterate, they have no education, they live in hovels. What do they know? They must be making this up. So, as I said, meteorites at best were seen as mere scientific curiosities. They weren't studied, they weren't collected, they were just lost or destroyed, or they just disappeared. Until 1794, when this chap, Ernst Chladni, who was a German polymath. He was an amazing musician. He was an amazing mathematician. In fact, he wanted to be a professional musician, but he was from quite a well-to-do family. And at that time, music was not seen as a sort of suitable occupation, so he was forced into the law by his family. But he actually turned out to be quite a good lawyer. And because of his great interest in reading and with his legal training, he started reading the few accounts that had been recorded of meteorites landing. And he was also actually able to interview in person a few people who claimed to have seen meteorites land. And he worked out that all of these stories, so ones from history, contemporary accounts, whether they were from France or Germany or Italy, were all describing the same phenomenon. So loud noises of explosions, maybe seeing a fireball, a stone landing, sonic booms, things like this. And he said, well, something's going on here. Why would all of these people who are lying or don't know what they're talking about, why would they all be describing the same things? You know, using my legal training, there's got to be something in this. So he actually got hold of some pieces of these materials, these meteoric ions, as they were called, and he actually did a study of them. And he wrote the first well-received, it wasn't actually well-received, but certainly the first well-read paper on meteorites. And you can see here it's called On the Origin of the Mass of Iron Found by Pallas and Other Similar Iron Masses and on a Few Natural Phenomena Connected Therewith. And so this paper was published in 1794, and it had some major conclusions. So he said, well, actually, yes, you do get these masses of iron and stone falling from the sky. This does happen. These people are not making this up. Fireballs associated with the fall of these objects are due to frictional heating of these things coming through the atmosphere. And these are the critical conclusions, that these, sorry, I've just seen a typo there, these solid bodies are unrelated to the Earth or the Sun. And this was a very important conclusion because the few scientists who did sort of grudgingly admit that maybe meteorites could fall from the sky said that they must be from the moon. And at that time, the Earth-Moon system was considered a closed system, and so they were considered to be sort of one and the same thing. So the fact that he said they're actually unrelated to the Earth, brackets, and the Moon and the Sun was a major conclusion, and he said, right, these have to come from cosmic space, and they must be small bodies that never accumulated into planets, fragments of planets disrupted by explosions, or fragments of planets disrupted by collisions. Now, what we know today is he was right on the first one, so well done, Chladni. Not so much on the second, but he was right on the third one. So this was a really groundbreaking paper, and it did pique the interest of scientists around Europe, although most of them were very sceptical of his results, but at least it piqued their interest. So we fast forward a few years, 1802. Here we have some images of the UK's first recovered and preserved meteorite. This is Wold Cottage. It fell in Yorkshire in December 1802, And you can come and see this meteorite at the Natural History Museum. We actually have it in our treasures gallery because it is considered a treasure not only of the museum but a treasure of meteorite science, because it is one of the first meteorites ever to actually have undergone detailed scientific study. And it was done by this gentleman here, Edward Howard, who was a very accomplished chemist. If my memory serves me correctly, he was made a Fellow of the Royal Society when he was something like 22. Obviously, that doesn't happen today. I think you have to be more like 62. Anyway, so we have is anyone good at recognising faces? It's quite apt that we're in the Geological Society. Does anyone recognise the gentleman in the front of that image, this chap here? William Smith, exactly. And then this is William Allen, who was another accomplished chemist of the time, and there's Howard in the middle. So Howard did the first sort of what we would call proper chemical analyses of a number of these meteorites, about half a dozen of them, that were actually sort of recovered and made their way into private, usually, collections between the sort of late 1700s and very early 1800s. And he did that work in conjunction with a French mineralogist, Louis Comte de Bournon. Now, I can't find a picture of de Bournon, so I have a picture of Bournonite, which is the mineral named after de Bournon. That's the best I could do. Now, it's much clearer on my screen. Unfortunately, it's not very clear on the screen here, but this is actually a facsimile of the paper that Howard gave to the Royal Society. And this was at the request of Sir Joseph Banks, who was the then president of the Royal Society. And he actually tasked Howard with actually doing the chemical analyses of these objects to try and work out actually what was going on. And what's quite interesting about it is the title of the paper that Howard was going to give was Experiments and Observations on Certain Stony and Metalline Substances which at different times have fallen on the Earth. And as with any junior scientist, even though he was a Fellow of the Royal Society, Banks insisted on seeing the manuscript before it was presented to the Royal Society. And Banks at that time was still not convinced that meteorites could actually fall to Earth from the sky. So he actually annotated it to say, adding in the are said to have fallen on the Earth. But actually we know now indeed that these were meteorites that were falling to the Earth, and these are Howard's studies are the first sort of acknowledged, some of the first acknowledged chemical studies of meteorites. And this is actually from the first edition of the Catalogue of Meteorites. So the Natural History Museum, we publish one of the definitive listings of meteorites in the world. We still publish this today, the Catalogue of Meteorites. It's actually on my list of things to do for the next 5 years, is get the next edition up to date. But I'll just read the first paragraph there. Until nearly 50 years after the establishment of the British Museum, so British Museum was established in 1753, meteorite collections nowhere existed, for the reports of the fall of stones from the sky were then treated as absurd, and the exhibition of such stones in a public museum would have been a matter for ridicule. So it just goes to show you that really meteorites and the study of meteorites as objects of scientific interest, and critically as objects that could tell us about what was happening in our solar system, really only kicked off in the sort of early to mid 1800s. And so actually it's quite a young science, it's actually younger than geology. So I think this is my first video. So if we can play the video, Gary. So anyone want to tell me what this is? Okay, so that is a video, well, that's some footage from the first atomic bomb, or the first atomic explosion on Earth, the Trinity test, that occurred in 1945 in the New Mexico desert. And you're probably thinking, why on earth is she showing video of an atomic explosion? Now, I'm not going to talk about meteorite impacts and the risk of asteroids or comets hitting the Earth. That's been done before, I know. But what I'm going to tell you about is this. So the development of the atomic bombs, the atomic weapons by the United States during World War II, as I'm sure you're all aware, was an enormous scientific and engineering effort by the Americans and the Allies as well. Obviously, the UK had an active program as well, which was subsequently merged with the American program, the Manhattan Project. But two of the scientists who were heavily involved with the Manhattan Project were actually physicists, cosmochemists. You know, at that time, many had sort of dual roles. And so the gentleman on the top left is Alfred Neer, who was he was a nuclear physicist and also a nuclear chemist, and he was instrumental in developing the technique of mass spectrometry, so to actually separate elements into their different isotopic components, the different types of isotopes, so light isotopes and heavy isotopes, using electromagnetic separation. And the gentleman on the bottom is Ernest Lawrence, who was again a nuclear physicist and has played a major role in understanding nuclear processes within stars, for example, in our galaxy. And they actually were instrumental in developing this big thing here. To give you, I want to try to find an image of somebody actually standing near it, but if a person was standing there, these things were about the size of height of a human, adult male human. And so they developed these things called Calutrons, which are actually, the name is from California cyclotron. And these were combinations of these things called cyclotrons and the mass spectrometers that Neer had actually developed to do scientific studies. And these were methods that were on an industrial scale to try and separate uranium into its different isotopes to actually produce fissionable products from which to make a nuclear bomb. Now, why has this got to do with meteorites? Well, both of these gentlemen, as I said, had studied meteorites prior to getting involved in the Manhattan Project, and many of the chemical and analytical processes that were developed to separate uranium into its different isotopes have actually been subsequently used by cosmochemists and geochemists to separate bits of meteorites into the different isotopic compositions so we can actually understand what's happening 4.5 billion years ago at the beginning of our solar system, and the process is a few millions of years and then billions of years after that. And Sarah might recognise the image on the top left. That's one of the clean labs at Imperial College with somebody actually doing some chemical separation, so dissolving up a meteorite into its component parts. And then we've got images there of mass spectrometers. So these are equipment that people like myself and Sarah used to use, and we're using these types of equipment today to actually study the real components, these tiny components of meteorites, to be able to give us that window back to 4.5 billion years when the solar system was first forming. And why are we doing that? Because we can look at a meteorite and we can see this is a scanning electron microscope image. It's actually false coloured. What we're seeing here is the concentration of different elements. We've given the different elements colours. So in this case, red is where there's lots of iron, green is where there's lots of magnesium, yellow is where there's lots of calcium, and blue is where there's lots of aluminium. And we're interested, for example, if we want to study our very first stages of solar system formation and what was happening, we're interested in studying objects like this. This is a particularly large one. This is where I slap my own hand. Sarah, what's wrong with this image? There's no scale bar. Well done, you see. I knew she was listening to me. There's no scale bar, but just I know this section very well. So this thing's actually about 2 to 3 millimetres across. This is quite large. And so what we're interested in is measuring the composition of elements like aluminium and calcium and magnesium within these types of objects, because that tells us about the very first stages of solar system history. And why is that interesting? We have another video. So Gary, if you can do your stuff. So this is a YouTube video. We've got some nice atmospheric space sounds in the background. And this is a beautiful video from NASA. It's an artist's impression of if we could go back in the TARDIS or in a time machine 4.56 billion years ago to when the solar system was first forming, this is what we think it would look like. And we understand this from combining the mineralogical and the chemical information that we've derived from meteorites using cutting-edge instrumentation that was developed partly as a result of World War II. We can use all of that evidence, we can combine it with information gathered by our colleagues using amazing telescopes like the Hubble telescopes, and we can get an idea of what was happening in our solar system 4.5 billion years ago, where we have the young sun, the vibrant, energetic, dynamic young sun surrounded by this disk of gas and dust that slowly clump together to form the planets as we see them today. And people say, well, that's nice. What's the point of that? So the top answer is, well, it keeps me in a job, so that's quite important. But actually, it's more fundamental than that. There's one thing that we know is unique about our solar system. Life, exactly. So if we can understand our solar system as much as possible, we can understand how it formed and how it is got to where it is today. We can apply that knowledge to other planetary systems and other systems in other galaxies and within our own galaxy today. And so if we are seeing the right sort of conditions that we've understood from our own solar system, it makes the chance of life elsewhere in the universe that bit more. So, oops, I need to go on to the next slide, which doesn't seem to want to go. How do I do that? Oh. No, I knew this would happen. See, this is modern technology. Could you move on to the next slide, Gary, without the video playing? Great. So we've got another video. Right, I realised we've missed one out here. So it's okay, it's not the end of the world. So what we're actually seeing here is the splashdown of the first Apollo mission, Apollo 11, that went in July 1969 to the moon, recovered the first lunar rocks. I can assure you we did go to the moon. It was not hoaxed.
The nation's response to this historic mission.
Some way, when those two Americans stepped on the moon, the people of this world were brought closer together. That it is that spirit, the spirit of Apollo, that America can now help to bring to our relations with other nations.
Okay, so I'm wondering actually, Gary, can we just play that again, maybe with the sound down? I feel terribly, I haven't got the controls, I have to rely on somebody else. So what I want to show you here, there's a few things I want you to notice. So there's the Apollo 11 capsule. This was the first mission to the moon, remember, and at that time there was a concern that the moon rocks and the astronauts might have caught moon bugs. And this was a big concern. And I'll discuss it a bit more. And we see here, oh, there they are. They've got these funny suits on. The door's been opened. One of the Navy divers has dived in, thrown in these suits, which you'll see the astronaut wear. Coming around now, you can see they're wearing this sort of suit with what looks like a gas mask on. And this was the way that was designed at the time to try and prevent contamination of the Earth by possibly harmful moon bugs. Maybe if we can go on to the next video, Gary, but this time with sound, please.
To protect against any possible lunar contamination, the astronauts put on airtight special garments before coming aboard the rescue ship. They transferred directly from the helicopter to a mobile quarantine van, in which they would be flown back to the Manned Spacecraft Center in Houston, Texas.
Okay, so I mean, as you can see, this was taken very, very seriously by the scientists and the authorities because there was a genuine concern that the Apollo astronauts and the moon rocks might be somehow infected with these, moon death bugs. Now, it was quickly seen that this actually wasn't the case at all, and in fact, after the Apollo 14 mission, Apollo 14 mission, they actually decided that they didn't need to do any of these contamination controls. There were no more risks. So the other astronauts didn't have to actually go into this quarantine facility, which, if my memory serves, I think the astronauts were in there for something like 3 weeks. Although allegedly the quarantine was maybe not as rigorous as it could have been, because they realised quite quickly that there was no harm associated with these moon rocks. So there they go, there's the astronauts in the quarantine facility, and you might say, well, actually, there was only 2 astronauts that walked on the moon, but all 3 are in the quarantine facility. Why is that? Well, of course, the two who walked on the moon, Armstrong and Aldrin, went back up to the orbiting spacecraft, and obviously were in contact with Michael Collins, who was the pilot of the orbiter. And so if they had caught any of these, moon death bugs, then they presumably would have infected him as well. So all three had to spend this time in quarantine, and they were all looking very happy there to see Richard Nixon. So, as I said, this is something that is taken very seriously by the space community, and it's something that I have a blessing and a curse myself to be involved with, because it's a rather contentious issue, although it's fascinating from both a scientific perspective and also from a philosophical perspective. And so there are very, very strict regulations on how we go about exploring our solar system, particularly if we plan to land anything on a celestial body, whether it be a robot or whether it be a rover, or whether it actually be a human being. But there are particular clauses and particular areas of concern and areas of interest if we ever plan to bring material back from those bodies. And when I say back, that includes people. And remind me to mention something at the end if I forget. So you can see this is Article 9 of the Outer Space Treaty. You might be able to read it. I'll pick out the main bits, but the main area that this article concerns is, as I said, when we go to a celestial body and potentially when we bring material back, so what we call sample return missions. And so we just take some of the language from that. So we're concerned with going to the moon and other celestial bodies and conducting exploration of them so as to avoid their harmful contamination. So this is where we want to avoid contaminating the place that we go to with Earth stuff. That we call forward contamination. And similarly, if we are bringing material back from those celestial bodies, we want to avoid, or certainly not have, any adverse changes in the environment of the Earth resulting from the introduction of extraterrestrial matter. And that's what we call backward contamination. And this is something that is taken extremely seriously, because what we don't want to have is that. We really don't want to be infecting the Earth with Martian death bugs or Phobos death bugs or cometary death bugs. And so the European Space Agency and NASA actually employ people whose role is Planetary Protection Officer. Can you imagine having that as a job title? What do you do? I'm the Planetary Protection Officer. In fact, I know both of them. There's only two of them, believe it or not. NASA's got one, ESA's got one. They're really great people, very, very interesting to talk to. And so we have these active research programs and active, actually sort of mandated programs. Both NASA and ESA and the other space agencies have them, and all of the nations that have signed up to the Outer Space Treaty will have people responsible for planetary protection if they are sending a mission to go and visit one of our solar system neighbours, because we have these people to make sure we don't have that. This is what we're wanting to avoid. And this actually has come out in films and TV programmes in the past, and indeed there's a film out at the moment, which I've still not gone to see, called Life. I don't know if anyone's seen it yet. In fact, that's quite funny because, again, if there's time at the end, I can tell you about that. But there's a fantastic book that came out in 1969, same year actually as the first, obviously, Apollo moon mission, or landed moon mission, I should say, by Michael Crichton, the famous sort of science fiction author. And Michael Crichton actually was a medical doctor by training. He was actually a very, very good scientist, and he wrote this fantastic book, The Andromeda Strain, which I first read when I was about 13. My dad had a copy, and I just pulled it off the bookshelf one day, and I can't believe that I read that, was fascinated by it, and now I'm actually working in this area. It's funny how things work out. And a film was made in 1971, and I've been able to locate the film trailer on YouTube. I've actually seen the film, and I would recommend, if you can get hold of a copy, you read the book and watch the film. It's one of those rare occasions where the book and the film are as good as each other. So if we can have the next slide, please, Gary, and with sound. This will give you a flavour.
Now, don't be scared. I'm a doctor.
Where am I?
A special laboratory in Nevada. We brought you here. You're sick.
In a true biological crisis, which our exploration of space could bring about, the present lunar receiving laboratory might prove inadequate. I therefore urge the establishment of a facility to deal specifically with an extraterrestrial form of life.
Seems to me, General, Dr. Stone put one over on you. In fact, he made us all think his wildfire lab could handle any contamination from outer space.
It's crazy. I didn't know buzzards fly at night.
Buzzards only come when something's dead.
Bando negative, Cable 1, what's happening?
We see bodies. Lots of them.
These people were cut down in mid-stride.
Everybody's dead! You did it!
I recommend calling a wildfire alert. All members of your team have been cleared and are now being called in.
If things get out of control, even you can't work miracles.
Grandpa, there's a car and they got guns.
What's going on?
This communication is being monitored.
Never believed this could really happen. You lose, Tommy. You knew it!
I didn't think it possible.
I wish I could believe you.
Whether you do or not, the only important thing now is to find the antidote.
Even with a microscope, they're blind.
I'm turning off the oxygen.
Experiment with your own life, damn it!
I'm scared. Oh, I'm scared.
Now, I bet you're all desperate to go home. But I really recommend you watching it because it's actually very scientifically accurate from the time, so in the late 1960s and 1969 when the book was published. And actually, many of the concepts are very similar to what we're planning for today. Now, I'm not saying that the UK or Europe is planning a 5-story building buried in the desert somewhere with a nuclear one spoiling the story. But actually, in terms of things like contamination control and the techniques that we would use to actually study materials coming back from space, in a contained environment, it's actually really quite frighteningly accurate. And I don't mean in terms of death bugs coming back, but in terms of the technology and the techniques it describes. And so I really would recommend you read that book and watch the... Oh, no, it's going to do it again. Can we go on to the next slide, please, Gary? Talk amongst yourselves. There we go. So I've been working for the last few years with the European Space Agency and also NASA looking at the exploration of Mars. I'm lucky enough to be involved with the PanCam team, which is an instrument on ExoMars, which is Europe's hopefully lander to Mars in a few years' time. But this is just a lovely image from the Planetary Society, which shows how many missions have gone to Mars. But I'm sure you're aware that it's very, very risky. There we go, I've managed to get risk in. It's very, very risky to go to Mars. And only about a third of the missions that have been sent to Mars have actually arrived at Mars and actually been successful. And obviously we've got some missions going on there at the moment. We've got NASA's MAVEN mission, which is an orbiter, which is tasked with looking at the composition of the Martian atmosphere. We also have ESA's Trace Gas Orbiter, which has got British scientists working on it. And we also have 2 rovers operating on the Martian surface. One of the Mars exploration rovers and the Mars Science Laboratory, also known as Curiosity, which are 2 NASA rovers. Amazing bits of technology. And the reason why we go to Mars is because it's very interesting. We have found out through different studies, including the studies of Martian meteorites, and again, if there's time at the end, I'll tell you an interesting story about that Mars had liquid water on it, and Mars quite possibly has liquid water existing in the right circumstances today. And water is a critical element for life, or a critical thing for life. So if you've got water, you've got a good chance of finding life. And so water really drives our exploration strategies for Mars in particular. And one of the things that we're looking at planning for is Mars sample return missions, because if you are wanting to send humans to Mars, you can prove technologies and you can have a look scientifically at the sorts of materials that they would encounter by going to Mars, picking up some rocks using a robot and sending them back to Earth. Now, this is quite a complicated thing to do. This image is from the Jet Propulsion Lab, and it's actually just an annotated image of the Mars Science Laboratory, the Curiosity rover, and it has lots of amazing science payload on it to work out the composition of rocks, using chemistry and mineralogy, work out the radiation environment. It even shoots laser beams out of its eyes to measure the composition of rocks, which I always think is pretty cool. And so it's got an amazing array of scientific kit. Now, this actual rover is about the size of a mini car, you know. So I mean, these are big things. They have nuclear power sources to power them, and they're really complicated, amazing bits of technology and engineering. Now, I mentioned Mars sample return. Why do we do it? Well, it's really the only way that we're going to be able to answer really amazing scientific questions that are going to be, again, fundamental to our understanding of life within our solar system and, by extension, life elsewhere in the cosmos. Now, Curiosity and the other rovers that have gone to Mars and have planned to go to Mars have amazing scientific payload on them. Fantastic. But it was never as good as the lab-based equipment that we have on Earth. And you cannot miniaturize some of the equipment that we would like to study these rocks. You simply cannot do it. And it really is going to be the next step of our exploration of Mars. But we have major planetary protection considerations because we do not want to inadvertently contaminate the area of Mars that we go to with terrestrial life. Because if we bring those rocks back, and the lab goes, oh, we found some bacteria in this, we want to make damn sure that that bacteria is actually from Mars and it's not stuff we've inadvertently taken with us that's hitched a ride on one of our rovers or one of our robots. Similarly, if there is Martian life, we don't want an Andromeda Strain situation. So we also have to make sure very carefully that if there is any life in those rocks, if there is any extant life, that life poses no hazardous to Earth's biosphere or Earth's environment. So very complicated to make sure that we're sending sterile missions, sterile rovers, sterile landers, and then when we bring those materials back, that we can handle them and study them in the safest possible way to avoid inadvertently contaminating the Earth with the Martian death bugs. And do I believe there's Martian death bugs? No. But we have to be very careful nonetheless. So many agencies are spending a lot of money and a lot of time on how to actually plan for this. And this is an image from a study that I've recently been involved with called IMARS, which was a joint NASA and European Space Agency study where engineers and scientists got together to try and work out how we would plan for a Mars sample return mission. These are highly complicated missions. They're also very expensive, and therefore it's almost certain, it's not definite, but it's almost certain that these are going to be international missions with different space agencies providing different parts of the mission. Not only does that actually mitigate the risk and mitigate the cost, it also means that you're getting the best minds, you're getting the best engineers, the best scientists from across the world working on these problems together. So you can see there's lots of elements for this. We call this the 4+1. So to get about 500 grams of Mars rock back to this thing, the sample receiving facility, which was the bit I was involved with, you need 4 separate launchers, and you need a rover, and you need another rover, and you need a mobile ascent platform. So it's quite complicated. So the engineers loved it. We sort of started going, I don't know what you're talking about, but it was a very interesting study to be involved with, just looking at the engineering complexity to get 500 grams of material back to Earth is something to behold, but it can be done. So this is just to reiterate the point. Here we have the Mars Science Laboratory, again, Curiosity rover with its different instruments. And the instruments that we have here, this is a laser ablation ICP-MS. Here we have a super-duper electron microscope. Down here we have an ion probe or a nanosims. Here we have a fantastic super-duper high-resolution transmission electron microscope. And here we have the diamond light source, the diamond synchrotron facility up at Harwell in Oxfordshire. And the reason why I'm showing you this is all the sort of lab-based techniques that we would use to study in more detail the same sorts of things that the Curiosity rover is actually studying today. But as I said, it's to reiterate the point, we cannot shrink down a synchrotron light source onto a rover. It cannot be done, which is why it leaves us no option other to, if we really want to study these samples properly, we need to bring them back to Earth and study them using the full array of the lab kit that we have available to us. Now, this is a screen grab from a few years ago that one of my colleagues in industry phoned me up, and he said to me, he said, "Do you read The Sun?" I said, "I don't think so." I used to read the News of the World. It was for the sport. That he said, he said, "I thought you might have put something on there as a joke." And I said, "No." So he sent me the link, and this was a reader's response to an article where Colin Pillinger had planned to send a fleet of beagles back to Mars to do various scientific experiments. So Sandra from Swansea says, as if enough new illnesses aren't being imported with so-called asylum seekers, they now want to risk bringing God knows what from another planet. Why can't these so-called intelligentsia leave well alone? Well, there you go. But, you know, I'm being tongue-in-cheek, but actually, you know, she has a point. People are concerned about the Martian death bugs. Nobody wants an Andromeda Strain situation happening, which is why I want to sort of, if you take one message home from this presentation, is that we are working very hard to make sure that all of the risks are minimised and completely mitigated, ideally. And so we're looking at various options about how we handle these materials. We're working with colleagues from Public Health England. So this is what used to be called the Health Protection Agency at Porton Down. That's a very interesting place. I've been there a few times. I can tell you some stories about that. But we are used to dealing with some of the most hazardous pathogens and hazardous materials on Earth. So some of my colleagues from Porton Down that I have been working with about planning how to study Martian rocks in a safe way were the same people who were out in Sierra Leone year before last, dealing with poor people suffering from Ebola. So we have the expertise there. We know how to handle these very hazardous materials. We have great experience from dealing with meteorites. These are two of the meteorite processors at the Johnson Space Center, handling meteorites collected in Antarctica in a very clean way, in an atmosphere of nitrogen, and to minimize terrestrial contamination and damage to those precious samples. We have great expertise from surgery about using robots. So I don't know if you remember in the Andromeda Strain video, you could see them using these big robots. That was the modern day technology then in the 60s. Now we can actually carry out microsurgery using robots. So we can actually have a situation where if we have a material that we think might be hazardous or is hazardous, we don't even have to be we don't have to be anywhere near it. It can be handled and it can be studied using robots as our eyes and ears and our hands. So we have amazing links with the high technology robotics industry. And then we have great experience of working in ultra-clean environments. This is a lady, Dr. Eileen Stansbury, who's a very dear friend of mine. She's the chief scientist at the Johnson Space Center in NASA, and she was instrumental in making NASA's cleanest clean room. And this clean room was made specifically to put together the collector for the Genesis mission. The Genesis mission was a NASA mission in the early 2000s to go and collect particles of solar wind. And she had to work a lot with scientists and engineers at NASA, but she also worked extensively with people from the semiconductor industry and the pharmaceutical industry, again, who have to work in extremely clean conditions. So we can use all of this knowledge gathered from industry and other areas to bring in, and similarly we can spin out technologies and ideas to industries that have nothing to do with space exploration, but have linkages there because we need to do the same sorts of things. So I realise I'm nearly at the end of time. So we're looking at our solar system exploration now and in the future. You've heard some of the recent past, some of the stuff that we're planning to do. This is a recent mission. This is an image of the Hayabusa robot. This was an amazing Japanese mission to an asteroid called Itokawa. It had the most terrible engineering problems. The mission nearly failed on a number of times, but the amazing Japanese engineers were able to actually get it to do what it needed to do. And it visited this amazing asteroid, Itokawa, in the asteroid belt, and it actually collected for the first time ever samples of the surface of that asteroid. This is not an image of it doing its thing, but this is an artist's impression. It took, for the first time, some amazing images of what the surface of an asteroid looks like. So this is one of the images. You can see the scale bar here is 10 meters across, so you can see a sort of mixture of what looks like quite fine, dusty surface and material that's a lot more rubbly. If we go a bit closer up, the scale bar this time is about 1 meter across, and you can see not really dusty, it's actually really lumpy and rocky, and you've got sort of flat rocks and sharp rocks and rounded rocks. So again, this is the type of information that we're using now when we're looking at how we're going to collect how we're going to collect samples from asteroids, because ESA and NASA are planning or have missions to actually collect surface samples of asteroids. So we need to know what it is that we're actually sampling. Do we need a drill? Do we need a scoop? Do we need something else? How are we going to actually collect this material? This is what happened when the material from Itokawa came back. So we have two of the Japanese colleagues there actually with the sample return capsule. This is in the Australian desert, and they're wearing, you can see, sort of bomb disposal type kit, because actually there are explosive bolts on this, and so to make the spacecraft safe before it could be handled by the people who hadn't had the explosives training, they had to go and diffuse all of the explosive charges that were left on the spacecraft, or on the spacecraft return capsule. I'll just very quickly tell you a story about this. So I was speaking to one of my colleagues at the Japanese Space Agency, and he was telling me that, so this landed in the Woomera Test Range in South Australia, and they actually had to have two tribal elders from the local Aboriginal community with them, because it's seen as it's a local it's a tribal area, it's Aboriginal land, and if the thing had landed anywhere near water, then they would have had to send women in to basically sort of do the spiritual stuff before the scientists could actually go in and recover the capsule. So that was obviously seen as being very, very important to make sure that the local community understood what was happening and to make sure they were happy with what was actually going on. As it was, you can see it was a very dry area, but before the scientists went in to recover this amazing capsule, they received permission from the local tribal elders that they were able to do so. So you don't think about things like that when you're planning space missions, but now we do because of that. So this is how the Japanese store these samples from the asteroid Itokawa, just to give you an idea. These are the little drawers that they store them in. That's about, 3 or 4 centimetres across. I store meteorites in cupboards that are about this wide and that high. So curators like storing things in drawers. They store their stuff in little tiny metal drawers. I store my stuff in big wooden drawers, but we still store it in drawers at the end of the day. But they store it in this. So those little drawers are in this amazingly sort of fancy-looking chamber. So this is a chamber that has no oxygen in it. It has no moisture in it. It's the composition of the nitrogen gas that's in that is checked all the time. It's being constantly checked for contamination, terrestrial contamination that could be creeping. This in itself is in a very, very clean room that is limited access to get in. I've been privileged enough to be in that clean room, and you have to get fully suited up in all your clean room kit before you go in, not wear makeup, not wear deodorant, things like that. So it's a really amazing thing to actually see. And to be honest, this image does not do it justice. I mean, it really does look like something out of a science fiction film, completely designed and built to order to curate about 1,500 grains, about 10 microns across. So it's quite amazing to think. I think this is the last video, Gary. This one doesn't have any sound. So this is a sort of artist's impression, computer-generated images of the NASA Cyrus Rex mission. So this is the mission that NASA launched in September 2016, and I was greatly honoured to be invited by NASA to go to Cape Canaveral to actually watch this launch. It was outstanding. And this mission is going to visit the asteroid Bennu. It's a B-type asteroid, very interesting, some of the most primitive material in our solar system, full of organics, full of all of those chemicals and molecules that we think are the building blocks of life. It's going to collect anywhere up to 2 kilos of material, so that's pretty good. We're quite excited about that. Its nominal amount of material to collect is 60 grams. If it gets 2 kilos, great. And it will return that precious sample to Earth in 2023, so not much longer to wait. And, well, you laugh, but I mean, it really, in sort of space science time, that's quite quick. And actually, we're very lucky in the UK that we have scientists actively involved in this mission. So we've got great UK representation in the Cyrus Rex mission. So I've realised I'm bang on an hour and haven't left much time for talk, so I'll let you read those. But one of the things I want to emphasise is that we have learnt so much from our solar system through the study of meteorites, and by using modern technologies, both to study meteorites, but also to apply what we know about meteorites to the payloads that we're sending on robots and rockets, to actually do those in situ studies, and then that material hopefully to come back to Earth so we can use the same techniques. The whole thing is a great virtuous circle. There's lots and lots of linkages with other areas of science, other areas of industry and engineering. They can give us advice, we can give them advice. But one thing that I'm very, very proud of is that the UK has and continues to lead in the science in this area, and also the engineering and the technology development. We punch well above our weight. It's acknowledged internationally that we are very, very good at what we do, and I think it's something that we should be very, very proud of, and something that I hope you as taxpayers, I also pay my taxes, I have to say, but us as taxpayers, I should say, you should be very, very proud of that the UK has supported this area and continues to support it. And if you have any links with government, or if you know any MPs, you make sure you tell them to continue to fund space science in this country, because it's something we're actually very good at. And thank you very, very much for your attention.
Brilliant. Thank you very much, Caroline. I've decided that I know what I want to be when I grow up, and that is a planetary protection officer.
Yeah.
Oh, yes. I think we've got time for 2 very quick questions. Any questions? Yes, sir. If we just wait for the microphone.
I know this, Jen, sorry.
There is just one question I do want to put to you. It's 2 parts, really. First of all, let me emphasise that explorations, bringing stuff back, I think it's great, and I wish we could do more of it. But the first part of the question is, the risk of sounding, the meteorites that come from Mars, you are absolutely sure 100% that they do come from Mars.
Yes, that is a completely different talk. Okay.
Oh yeah, I'm not. But just going past that, you are absolutely sure they come from Mars.
Absolutely.
Yeah. Okay. So, which brings me to my second part of my question is, you emphasise the enormous difficulties of getting a spacecraft to Mars and bringing it back, and you also said, of course, stuff in situ on Mars can't match the, shall we say, analytical ability of stuff that's here on Earth. If we've got stuff already from Mars, which we know is from Mars, here already, why go to all that expense to get something back from Mars when we've got it already? And I'm not saying we shouldn't do it, but I'm just thinking...
It's to keep me in a job. That's the main one. I'd say it's a valid point. So there's a number of ways I can answer that. So the first thing is, yes, you're right. We've got meteorites from Mars. We've got about 160 known meteorites from Mars out of about 56,000 known meteorites. So not very many, but enough. Now, the problem is that we don't know at the moment exactly on Mars where those meteorites are from. We can't pin them down to a specific crater on Mars or even a specific region of Mars. We've got a rough idea in some cases, but we can't say... So the way I would describe it is it's something to say, right, describe the geology of the UK to me and the geological history of the UK by collecting a rock from the Lewisian, a rock from the southwest of England, a rock from Norfolk, and a rock from Staffordshire. How can you properly describe the geological history and the dynamic stratigraphy of the UK using 5 samples? You can't. So what we need to do is we need to get a better idea of what's actually on Mars. And the only way we can do that is by sending a mission that combines a rover-like curiosity, so a robotic geologist where we can drive around and we can go, oh, that looks like an interesting outcrop, let's go over there. Oh, look, that's got bedding planes in it. Oh, look, that's got these structures in it. Collect those samples and then bring them back to Earth. The whole thing is this overall geological context. So the Martian meteorites are great. They have told us a lot about the history of Mars and Mars's geology, but it's only a tiny, tiny fraction and a tiny snapshot. We don't have any sedimentary rocks. Sorry, we don't have any sedimentary meteorites from Mars, yet we know there are sedimentary rocks on Mars. The Curiosity rover is currently analysing sedimentary rocks on Mars, so we're missing out on those important rock types. We also think we are missing igneous rock types from Mars that are not recorded in the meteorite record. So we know there's a huge amount of geology that needs to be done, and then similarly that sort of geochemical analysis that needs to be done. And the best way to do that is to go to Mars, do your geology field work, identify your interesting specimens, and bring them back to Earth to be able to study.
Thank you.
Caroline, would you like to choose your final question?
I think this lady here at the front, she had her... Oh.
You've talked about the risks of bringing back human pathogens.
Closer.
You've talked about the risks of bringing back human pathogens. I find it difficult to imagine whether you're looking for things which are fundamentally similar to the pathogens we already know, or are you looking for something that might be so different that we might find it enormously difficult even to recognize it when we've got it?
That is a great question. Now, I'm going to sort of preempt myself by saying I am not a biologist, okay? But my colleagues at Public Health England, formerly the Health Protection Agency, are experts in identifying new pathogens. Now, we're very confident that from what we know about Mars, what we know about its formation, what we know about its environment in terms of its chemical environment and its physical environment, the chances are it is similar enough to Earth that any life that evolved on Mars, whether it be in the past or whether it's still there now, is probably very Earth-like. And that actually is one of the problems, is because how would we distinguish between something that is genuinely Martian and something that is maybe we have taken it with us and then it's come back? So it is a very, very difficult thing. How we can determine it, there's various ways that have been suggested. And that gets down into things like molecular biology, so looking at things like DNA, the types of amino acids that are present in a living organism, the abundances of those different types of amino acids, if they're sort of enriched in some, whether they're left-handed or right-handed, all of these sorts of things that we can use to identify extraterrestrial amino acids from terrestrial amino acids. But it is a real question, and it's one of those questions that we discuss in scientific meetings, and it's one of those questions that often that discussion continues, you know, in the pub or the restaurant afterwards, saying, well, how would we be able to tell? And I'm confident that we would be able to tell if it was genuinely Martian or whether it was a terrestrial pathogen. But hopefully it won't be a pathogen. It will just be something completely harmless.
Brilliant. So thank you very much. I know that some of you unfortunately need to leave us to either go back to work or to enjoy a lovely evening. Thank you very, very much, Caroline. Absolutely fascinating. Thank you. Thanks, everyone. One down. Didn't manage to swing it. No swearing. You're very welcome.
Most impressive.
Oh, good. I'm glad you enjoyed it. I know, and without swearing or saying anything inappropriate. That's what I'm amazed about.
These microphones are probably still.
No, I'm glad you enjoyed it. It's such a.
As always, it gives more questions.
Well, absolutely. Yeah, it's a fascinating subject, and but it really is. And what I really enjoy about it, especially the work that I've been involved with things like Mars sample return, is this philosophical thing of, well, you know, if we were to find something, how would we recognise it was Martian? So one of the things that I didn't mention with the planetary protection rules are